Hello everyone, and welcome back to our journey and exploration of the realm of the set of complex numbers. Today we're going to be continuing our exploration of defining functions that are analogous to their real number counterparts, in particular powers and just basic roots, which are eventually going to build into radicals, polynomials, and also rational functions as well. So let's just do a quick recap of the things we've built up to this time, for which I'm going to assume you're already comfortable with. So I'm going to assume that everyone knows what the set of complex numbers is and how you define operations between complex numbers such as addition, subtraction, multiplication, and division. The second thing I'm going to assume is that you understand that a complex number can be represented in one of two forms. Its rectangular form, x plus iy, x is real part, y its imaginary part, I is the square root of -1. Or its polar form, r e to the I theta, r its magnitude, theta its argument. Last time in particular we defined two functions, the exponential and the logarithm. So we define e to the power of z, we define this to be equal to e to the x times cosine of y plus I sine of y, which on the surface may seem very, very strange, but if you sort of followed along with us, you're like, oh yeah, this is actually probably one of the more better definitions that we could apply to e to the z because it gives us a lot of the same properties as we did in the set of r. And from it, you're like, okay, well maybe we can also define the natural log of z, and indeed we can. So we came up with the definition that the natural log of z will be equal to define to be the natural log of the norm of z. So I'll just write it as the natural log of the norm of z. And that subscript 0 just means it's going to be the typical natural logarithm that takes place in the set of real numbers, since the absolute value of z is always going to be a real number greater than 0. And then we're going to have I times the argument of that number z plus 2k pi I, where k is an integer. And you might be thinking, why do we have k in the set of integers? Why do we have infinitely many outputs for one input z? Well, keep in mind e to the z was periodic, and this actually was the period of e to the z, which made e to the z complex exponentials very different from the real value counterparts, because e to the z is periodic, making it not one-to-one, which means its generalized inverse is not going to be a univariate function like it was in the set of reals. Right, so those are some of the things that we've built up to this point. Now let's go through a quick example of some basic calculations that I do definitely expect you to be able to do at this stage. So let's assume that we have the complex number z is equal to 1 plus I. So you might want to pause this video and see if you can find the argument, the magnitude, and also the natural log of this complex number, and also the principal value of the natural log of this number as well. So what will this be? So since 1 plus I is going to be located in quadrant 1, it kind of looks like that. Its real part is 1, its imaginary part of 1, and its magnitude is going to be the square root of 2, and its angle, pi over 4, 45 degrees. So if that's the case, then what do we have? So e to the power of 1 plus I will be equal to, again, e to the 1 times e to the I, right? That's one property that we get from defining complex exponentials in that way. So this is going to be equal to e times the cosine of 1 plus I times the sine of 1, and that will be equal to e to the 1 plus I. It's very important to note that you should not get this confused with the square root of 2 times the cosine of pi over 4 plus I times the sine of pi over 4. It's not r times cosine theta plus I sine theta, because that's not what this is, right? And you should be able to verbally explain why these two are not equal to each other, and this is its true form. Right? So that's the first thing. That's what e to the 1 plus I is. Now let's figure out what the natural log of 1 plus I is. So the natural log of 1 plus I will be equal to what? So that's going to be the principal value of the square root of 2, its magnitude, plus I times its argument, pi over 4, plus 2k pi I, where k is an integer. We can clean this up in a variety of ways. The square root of 2 has power of 1/2, and we can bring that in front of the log since that's one of its properties. So we have the principal value of the natural log of 2, and then we can clean this up by factoring out an I out of the right-hand side, let's say. And let's do pi over 4 plus 2k pi times I. And here k is a integer. All right, so that's what the natural log of 1 plus I is in its full form. And then from here we can find the principal value of the natural log of 1 plus I. So the principal value of 1 plus I is just the same, but taking k to be equal to 0. So this is going to be equal to 1/2 times the principal value of 2 plus pi over 4 plus 0 I. Don't forget the I at the end. So that's going to be the principal value of the natural log of 1 plus I. Right? So now that we know some basic calculations in the world of complex numbers, in particular exponentiation and logarithms, now let's see if we can define some other objects. So let's build our machinery. So let's assume that z is equal to x plus iy, or equivalently re to the I theta. And let's start by defining n to be equal to a natural number. You can include 0 if you want, but it's usually viewed as a special case. How would you define z to the power of n? Well, z to the power of n, if we take its rectangular form, is going to be equal to x plus iy to the power of n. So how would you define this? Well, one way you could define this is to use the binomial expansion theorem. So it can be like, oh, that's just going to be equal to the sum from k is equal to 0 to n of n choose k. So that's a binomial coefficient, x to the power of k, and then iy to the power of n minus k, right? So that's coming from the binomial expansion theorem, but it's complicated. It's complicated, but it works nonetheless, right? But is that how we really want to define z to the power of n? Actually, no, there's a nicer way. So we have the alternative. If we look at the polar form, z to the n will be equal to e to the I theta to the power of n. So this is reminiscent of the Domov theorem for complex numbers. And that's going to be equal to r to the n times e to the I n theta. And you're like, oh, that actually looks nice. So this is more nicer. So more nicer. And it's more useful as well. Right, so if you want to define z to the power of n, you could either do it in the rectangular form or you could do it in the polar form. Either one is fine, you get the same answers, but the polar form usually, not always, but usually is going to be a little bit more easier to handle. So let's actually go through a few properties to sort of make sure that we see why this is actually a lot more better. So firstly, let's assume that the norm of z is equal to 1. So what happens when you exponentiate z to a power of n? Obviously, it will not change its magnitude. And why will it not change the magnitude? Because r to the n will be equal to 1 to the n, which will be equal to 1, right? For all powers of n. The second case, if the norm of z is less than 1, then z to the n will have a smaller magnitude. For example, if the norm of z is equal to 1/2, then I'm going to have 1/2 to the power of n, which is going to be equal to 1/4, which is smaller than it used to be. And thirdly, if the norm of z is greater than 1, take a guess of what will happen here. It will have a larger magnitude. For example, if your norm is 5 and you square it, then it becomes 25. So it becomes longer, right? So keep in mind, when you operate on a complex number, and a complex number has two quantities, a magnitude and an argument, when you exponentiate a number to a power such as 2 or 3 or 1/2, you're not just changing its magnitude, you're also changing its argument. So the more interesting and fascinating thing about powers in the complex world is that powers also can rotate. It can rotate complex numbers about the origin. And this is actually quite interesting. So if you look, let's just take a quick example. Suppose we have 1 plus I, which keep in mind is the square root of 2 times e to the I pi over 4. And you're like, okay, well, where is this complex number? Well, this complex number is located right here, let's say. And keep in mind it has a norm of the square root of 2. But when we power or square this particular number, you're going to get the square root of 2, which is going to be equal to 2, and then e to the I pi over 2. And where is this number? Well, this number is going to go from, well, keep in mind, the square root of 2 is approximately equal to like 1 point something, and 2 is just going to be equal to 2. So if we expand this grid just a little bit, let's assume that this number right here is 2, right? Obviously bigger than the square root of 2, then your result is actually going to be right here, right? So this is going to be what 1 plus I squared is equal to, and this orange is what 1 plus I is equal to the power of 1. So notice that, yes, it has gotten bigger, but it's also rotated to the left, or in some sense counterclockwise, by pi over 4 again. So it's done pi over 4, and then another pi over 4 from just y is equal to, or x is equal to the square root of 2. Right? So it's gotten longer, and it's also rotated a little bit from what it used to be. Right? Also, what's so special what 1 plus I squared? It actually has a nicer representation, because keep in mind this is going to be equal to 2 times cosine of pi over 2 plus I times sine of pi over 2. And what is this? Well, the cosine of pi over 2 is going to be equal to 0, and the sine of pi over 2 is just going to be equal to 1. So this is actually just going to be equal to 2i. Right? So 1 plus I actually doesn't look like a nice number, I guess you could say, but once you square it, it becomes a nicer number because its real part kind of disappears. So we see that 1 plus I squared is just going to be equal to 2i. And there's two main takeaways from that explanation, is that 1, it gets longer, and 2, it rotates by a particular angle. Now, obviously, we don't have to only exponentiate by a power of 2. We can do cube to the power of 4, 5, 6, 7, 8, 9, 52 if we really want to. So what was theta for 1 plus I? Well, keep in mind that was just pi over 4. And then we squared it, and it becomes pi over 2. So when you square it again, that pi over 2 is going to be multiplied by 2. That's just going to be equal to pi. And then to the power of 6, that's going to be 3 pi over 6. Pause the video and see if you can figure out what these next two numbers are. But the next one's going to be equal to 2 pi, and then if we just do it once more after 8 to 9, that's going to be 2 pi plus pi over 4. And keep in mind that these angles, pi over 4 and 2 pi plus pi over 4, these are coterminal angles, right? Which can be viewed as equivalent angles from some particular thing. But if you think about it from the multivariate perspective, such as logarithm, technically they're on different branches. It's kind of like a floor above. So for example, if you think in a building, you're at the same exact position, theta, but you used to be here, and now you're one phase or one level or one rotation, quote unquote, above it. Right? So we have these coterminal angles of pi over 4 and 2 pi plus pi over 4. So what can you tell me about 1 plus I and 1 plus I to the power of 9? Are they the same number? No. But they're angles. For example, because keep in mind the absolute value of z, where z is equal to 1 plus I, was equal to the square root of 2. But the square root of 2 to the power of 9 is the same as 2 to the power of, 9 divided by 2, which is at 4.5, right? So that's 4.5, which is a lot longer than that, right? So pretty much what you see here when you exponentiate things, you go here, and then here, and then here, and then here. It's almost like a spiral, right? So for example, you do hit the same exact angles, but you get longer and longer and longer and longer, right? If you exponentiate and exponentiate and exponentiate. And keep in mind, since our norm is bigger than 1, it's going to be getting larger and larger, so this is going to spiral outwards, all right? So now that we understand a little bit about what powers actually do to complex numbers, one, it changes their angle potentially, and another potentially changes their magnitude, let's look at a couple other subtle pieces of information. So let's assume z to the n is equal to z for some number n and z. Then what can you tell me about the norm of z? So if this is true for some n, then the norm of z should change, right? It should get larger, right? Provided that z is not equal to 1, right? So if this is the case, what values of z is going to make this true, right? So solve for z, right? So for example, if I say solve z squared is equal to z, or z cubed is equal to z, what type of numbers z will satisfy that particular equation? So if we look at this particular equation, then we should be able to see that the norm of z must either be equal to 0, or the norm of z will be equal to 1, right? Because keep in mind that these should be the same. So if the norm of z is equal to 0, what complex numbers will satisfy this? Well, obviously z is equal to 0 can be shown to be the only complex number that satisfies this, because keep in mind 0 to the power of n is equal to 0, so it definitely works. And now we have this, the norm of z is equal to 1, and there's actually infinitely many numbers that make this true. For example, we have 1 to the power of n is equal to 1. That's obviously true for all n in the set of naturals. We have minus 1 to the power of n is equal to 1. This is going to be true for all n that's even. We also have I to the power of n that's going to be equal to 1, which is going to be true for all n that is multiples of 4. For example, 0, 4, 8, 12, 16, and so on. So we actually have several different complex numbers that satisfy the norm of z is equal to 1. There's 1, negative 1, I, minus I, and so on for some number z. Right? So if we look at this from a geometric standpoint, right? So whereas our norm of z is equal to 1, so that's this. So the norm of z is equal to 1. So any number z that has a base point at the origin and tail point on the circumference of the circle will have that. So the only thing that really is going to distinguish between these numbers is that particular angle theta. So what value angles of theta will give us this property? So what do we want? So we want to find all z such that z to the power of n is equal to z, where obviously z is not equal to 0 because we already know that that's a solution, but it's a trivial one. Right? So that means what? So let's look at this particular expression in polar form. So what is z? So let's assume that z is equal to e to the I theta, right? And let's assume with this, and let's assume that the norm of z is equal to 1, because we can always stretch it out later if we really wanted to, right? So z is going to be equal to 1 times e to the I theta. So that means that z to the power of n will be equal to e to the I n theta. And we want these to be equal to each other because we want z to be equal to z to the n. So that means this must be equal to this. So let's just solve this particular equation for theta. So that means e to the I theta will be equal to e to the I n theta. And then we can take the natural log of both sides of this. So we're going to have the natural log of e I theta will be equal to the natural log of e I n theta plus 2k pi I. Right now, this is very important to keep in the back of your mind because we are working the complex plane, not the real plane. So every time you take the natural log, you have to include the periodicity of the exponential function. So we have this particular equation now. So now that they cancel, we're just going to be left with I theta must be equal to I n theta plus 2k pi I, k an integer, and we can divide both sides by I because I is not equal to 0, so we have theta is equal to n theta plus 2k pi. So we have this particular equation, so you should be able to solve for m. So we can see that n will be equal to, what will that be? Theta minus 2k pi all over theta, which I guess you could write also as 1 minus 2k pi over theta. right? So we have what n must be equal to in this particular statement. And keep in mind, k must be an integer. So let's actually go to a calculation example to sort of see what's going on here. So let's assume that we have z is equal to 3 plus 2i. And let's try and figure out what power of z do I need to raise it by in order to get itself back again. So z to the power of n equals z, what must n be equal to sort of cycle back to where we are? So keep in mind z is equal to 3 plus 2i, so that means r is going to be equal to the square root of 9 plus 4, which is going to be equal to, what is that, 13. Right? So that means z to the power of n being equal to z is only true if what? Well, n must be equal to 1 is the only way, because for n bigger than 1, the norm of z to the n gets bigger and bigger and bigger. So it will never cycle back, right? And that's a really, really big problem. So if we want to sort of find a problem where this can cycle back, what we can do is we can place this number on the unit circle by normalizing it. So we can consider, for example, z star to be equal to z divided by the norm of z, and you should be able to verify that the norm of this number will always be equal to 1 for any number z. Right? So what I want to do is I want to create a new number called z star, which will be equal to 3 all over the square root of 13 plus 2 all over the square root of 13. And now we have a number on the unit circle. So what is the power of n that I need to exponentiate this by, right? So this is my z star. And I want to power this to some power n, because this is going to rotate it counterclockwise. What does that n have to be in order for me to be at z star again, right? So what is this argument's theta going to be equal to? So theta is going to be equal to the arc tangent of 2 over 3, or 2 over square root of 13 over 3 over square root of 13. So that's going to be equal to approximately 0.58 radians, or approximately 33.69 degrees, right? So if z to the n is going to be equal to z, and I'm just using z star as z here, then that means what? That means n must be equal to 1 minus 2k pi all over the arc tangent of 2 divided by 3. So that's the value of n that needs to be true, which is approximately equal to 1 minus 10.6856k, right? Where k is an integer. Now, obviously, if we choose k to be equal to 0, then we're just going to be left with 1. That's your trivial solution, but we don't really care about that. So as long as you choose another integer k that's not 0, then you're going to find another value of m. So, for example, if we choose k to be equal to minus 1, then n would be approximately equal to 11.6856. So what does that mean? So if you take 3 divided by the square root of 13 plus 2 all over the square root of 13, and you raise it to the power of 11.6856, you will get approximately 3 over the square root of 13 plus 2 all over the square root of 13. And let's not forget our lonely little complex number I, right? So you're like, oh, that's actually pretty interesting. So if you have a number on the unit circle, eventually you will have the same exact argument, and this little formula that we have here will actually build that for you. So now instead of looking at, the norm of z is equal to z, why not just look at the norm of z is equal to 1, since we can always traverse or transform a z into a normalized complex number, or some people will call it a unit complex number whose norm is equal to 1. So what we want to do generally is suppose that we have z to the power of n is equal to 1. Now our goal is to figure out, okay, well, what numbers z satisfy? So what z satisfy this particular equation? Well, it's obviously the case that 1 to the power of n will be equal to 1, but nobody really cares about this particular equation. So if we were to solve this equation, we're going to have z to the power of n minus 1 will be equal to 0. And you might be able to realize, oh, I can factor that into z minus 1, multiply by 1 plus z squared all the way down to z to the power of m minus 1. And that's going to be equal to 0, right? So that's your typical factorization. So from this leading term, we clearly see that z equals 1 is a solution. But what about this? So does this factor over c? And the answer actually is yes. Right? You're actually going to have n minus 1 complex numbers that will satisfy that. So let's see if we can find what those numbers are without having to introduce any new machinery. So for example, let's assume that we're asked to solve z to the power of 4 is equal to 1. Pause this video and see if you can figure out how to find all 4 complex numbers z that make this true. So the first thing that I want to do is I want to represent z in its polar form, since that usually works a lot better in the realm of powers. So that's going to give us what? So let's z be equal to r e to the I theta. So that means that r e to the I 4 theta, once you exponentiate by the power of 4, will be equal to 1. So what numbers z will satisfy this particular equation? Well, if we take the norm of both sides of this equation, r e to the I 4 theta is equal to 1, you're going to have that the norm of r will be equal to 1, which means that the x and y values of z will satisfy x squared plus y squared will be equal to 1, right? So keep in mind that's usually what we refer to as our unit circle. Right? So from here we can clearly see where they are located. So that means all solutions of z to the 4 equals 1 satisfy the norm of z is equal to 1, but there's infinitely many of them, right? So that means the only thing that distinguishes them are their arguments. It's the only thing. So we have the norm, we just need their arguments, and then we know exactly where they're located. So let's figure out what their arguments are. So that means e to the I 4 theta must be equal to 1, which means that 4I theta must be equal to, so take the log of both sides of this expression, so the log of that, and don't forget the periodicity of the exponential. So it's going to be 0 plus 2k pi I, where k is an integer. So now we just need to figure out what are the solutions for this, and i.e. solve for theta. So once you divide both sides by I, we're going to have 4 theta will be equal to 2k pi. I's are canceled. So that means theta must be equal to k times pi over 2, where k is an integer. So these are our arguments for our solutions. So that means that z must be equal to, so if we have z to the 4th is equal to 1, so that means z must be equal to e to the I k pi over 2, where k is an integer. So these are all of our solutions to this particular equation. So let's actually look at a couple values of k. So if you look at k and then what z will be equal to, so let's do 0, 1, 2, and 3. So we already know that if k is equal to 0, we're going to have z is equal to 1. When k is equal to 1, we're going to have what? So I pi over 2. 1 can show that that's just going to be equal to I. And then we're going to have minus 1, and then we're going to have minus I. And if you do 4th, that's going to be equal to 1. But keep in mind that's going to be representable in terms of its period, because that's pretty much 2 pi. Therefore, you don't need to consider, because these are your only 4 solutions, because it's just going to repeat everywhere thereafter, because we're on a unit circle and the norm isn't changing. So it's going to pretty much, if you look at this graphically, right, so here's our unit circle. So there's our k is equal to 0, there's a k is equal to 1, there's a k is equal to 2, there's a k is equal to 3, and then it's just going to be rotating and hitting those 4 points over and over again. So those are going to be our solutions. And what's actually pretty beautiful about this, if you connect these points with a line, you actually get a square, which is actually very, 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 very pretty interesting. Now, another thing that I want to mention before I give you this last example, when people say z to the fourth is equal to 1, I'm like, oh, solve for z. Most people be like, oh, let's take the fourth root of both sides of this equation. So let's take the fourth root of z to the power of 4, and then the fourth root of 1, and people are like, oh, the fourth root and z to the power of 4, they cancel, leave them with z, and then we're going to have the fourth root of 1, which is going to be equal to 1, and then the only solution is this 1. Yes, it is a solution, but there are 4 others. So there are more solutions. So what is so special about this one? Well, that's obviously our principal solution to this particular equation, right? So some people will call this the principal root, and we'll talk more about roots in a later video, but this is the principal root of 1, right? So 1 is the principal fourth root of 1. So let's introduce a bit of notation here, since obviously roots are an important part of this conversation. So if z to the fourth is equal to 1, then we're going to have how many roots of this equation? We're obviously going to be having 4 of them. So I'm going to create this new function, which is going to give you the fourth roots of z to the power of 4, and that's obviously going to be equal to z, and that's going to be equal to the fourth roots of 1. Right? So these are going to be the solutions of this equation. So if z to the fourth is equal to 1, then you can fourth root both sides, but keep in mind it's going to be multi-valued due to the nature of exponentials and logarithms. So our solutions are going to be represented as this function, right? So this is a multi-valued fourth root function. So this is a multi-valued fourth root function. So now we can use this function and find solutions without hesitation. So that means if we want to solve this equation, we can be like, okay, z is just going to be equal to the fourth root of 1, which by definition is just going to be equal to e to the power of what? So that's going to be equal to 2k times pi over 4. From our calculation. So 2k times pi over 4, which we already know is going to simplify, but I'm going to just leave it like that. So if I ask you, okay, what are all of our solutions for this equation? So we'd be like, okay, the first solution, the fourth root of 1, the principal one, is just going to be equal to 1, which some people will just denote as this notation, right? So this notation is just going to be defined to be equal to this particular object, right? So that's usually what we refer to as the principal fourth root of 1, which we commonly refer to as 1. But there are other fourth roots of 1, not just the principal one. So we can also say, okay, well, what are the other 3 solutions? So we're going to have the first principal, or the first branch, not the principal branch, but the first branch counterclockwise of 1, and that's going to be equal to I. The next solution of 1 will be equal to minus 1, and then the next one will be equal to minus I, and those are going to be our 4 fourth roots of 1, which some people usually refer to as the fourth roots of unity, right? So that's that. So now let's actually take a look at a common example that people get so mixed up in the early stages of math, and let's consider the equation z squared is equal to 1. So using the same exact notation, the same exact idea, well, what will be the solutions? Well, z will obviously be the square roots of 1. Obviously, the square roots of 1 is multi-valued, so this is going to be equal to what? So that's going to be equal to e to the power of 2k pi over 2, following the same exact idea, which is going to be equal to e to the power of k pi, where k is an integer, right? So z equals k pi is the solutions of this equation. And keep in mind, well, what is e to the k pi? Well, e to the k pi is going to be equal to the cosine of k pi plus I times the sine of k pi. But you should already know that the sine of k pi is going to be equal to 0, and the cosine of k pi will alternate between 1 and minus 1. So this is going to be equal to minus 1 to the power of k, where k is an integer. So it's going to be 1, minus 1, 1, minus 1, 1, minus 1, and so on. So therefore, if z squared is equal to 1, that means z will be equal to the square roots of 1, which will be equal to minus 1 to the power of k, where k is an integer. And then we can start choosing the principal root and the next root in sequence. So therefore, in particular, our two solutions, r2, 0 and r2, 1, is going to be equal to minus 1 to the power of 0 and minus 1 to the power of 1, which will be equal to 1 and minus 1 respectively. But sometimes people will use a different notation and say, oh, this is just going to be equal to the square root or principal square root of 1, which some people also write as that, right? So some people refer to this as the principal square root of 1, but keep in mind there are multiple roots of 1 under the power of 2. There are actually two. There's the principal square root of 1, and then there's the, I guess you could say, the secondary square root of 1. Right? So let's just look at one more example just to make sure we understand this multivaluedness of radicals. So let's assume that we have z to the power of 5, which is going to be equal to 1. So what are the solutions to this equation? Well, the solutions is going to be z is equal to the fifth roots of 1, which is going to be equal to e to the power of 2k pi over 5, where k is going to belong to the set 0, 1, 2, 3, and 4. Right? So those are going to be what we call the fifth roots of unity, right? So you can actually find them, and obviously we have one of them, in particular 0, that we call 1. But the other ones are not going to be as nice, but actually they're very, very beautiful. So since it's equal to 1, that means the norm of all of them is going to be equal to 1. So what I want to do is I want to just sketch a unit circle here. Right, so there's our unit circle. And then we're going to have how many solutions? We're going to have 5. So our first solution is going to be located here. Our second solution is going to be located approximately there. There's your third, there's your fourth, and then here's your fifth. So what is this? So keep in mind what we're actually going to be doing is we're going to be rotating by 2 pi over 5, right? Because this is going to be k times 2 pi over 5. So every time we exponentiate by 1, by 2, by 3, by 4, we're rotating by 2 pi over 5. So if we look at this particular angle here, this is 2 pi over 5. And then when we exponentiate again, that's going to be another 2 pi over 5. And then when we exponentiate it by another power, that's going to be another 2 pi over 5. And then once we go again, that's going to give us another 2 pi over 5. And then once we do one more 2 pi over 5, we're going to be back where we started, right? That's k is equal to 5. And you could also do the other ones, for example, -1, -2, -3, and -4, and -5. And again, it's going to still lock onto the same exact positions. Right? So what happens when you actually connect these points together? So if you connect these points together, you're actually going to get a shape that should look very familiar to you. You should see that this is a regular pentagon. It's a regular pentagon, right? With vertices on the unit circle. But these points here, in particular that one and that one, these are what we call the fifth roots of unity, whose analytical forms can be represented in terms of e to the 2k pi over 5, which is actually very, 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 very useful, right? And let's actually not forget that there should be an I in front of that particular statement. I actually think I forgot my I on my previous statement. Yeah, there should be a I in front of that one as well. So let's not forget our little i's, right? But that thing in front of that I, those are going to be our angles theta, so it's going to be I theta, right? So our fifth roots of unity form our regular pentagon on the unit circle, and then we have this one, z is equal to 1, which some people will abbreviate as this one, and that's usually what we call the principal fifth root of 1. But how many fifth roots of 1 do we have? Not just the principal one. We have 5 of them. We have this one here, which is k is equal to 0. This one here, k is equal to 1. K is equal to 2. K is equal to 3. And k is equal to 4. where each of them, z, can be represented using this new notation as the fifth roots of 1, whose ID or index for that root is represented by k, where k ranges from 0, 1, 2, 3, and 4. Right? So that's actually some of the beautiful things that you immediately see when you start to investigate the world of complex powers and also complex radicals. But there's plenty more to be discussed, which we will do in the near future. So I hope you enjoyed this video, and I'll see you in the next one in our journey through complex analysis. See you.